Hello, am I audible? Hello, hello. Can anyone confirm in the chat if I am audible?
Yes, sir, you are audible.
And is my screen visible? Is my screen visible to everyone? Okay, thank you. So good evening everyone. Welcome to this NPTEL live session for the course Introduction to Machine Learning. So this is my fifth live session. My name is Awan Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So in this live session, we will discuss some practice problems on week 5 topics, which were neural networks and parameter estimations. And I will also try to answer your questions and doubts. If you have any questions and doubts regarding any of these topics, then you can ask me later. First, we will discuss some practice problems on this. So this is the first question. So you can write your answers in the chat. This is on neural networks. So which of the following are correct? A perceptron will learn the underlying linearly separable boundary with finite number of training steps. Option B is XOR function can be modeled by a single perceptron. Option C is backpropagation algorithm used while estimating parameters of neural networks actually uses gradient descent algorithm. And last option is the backpropagation algorithm will always converge to global optimum, which is one of the reasons for impressive performance of neural networks. So multiple answers might be correct in this case. So you can write your answers in the chat. So Shankar Lal is saying A and C. Okay. Akriti is saying A. Anyone else? Any other answers in the chat? So the correct answers here are A and C. So Shankar Lal has written the correct answer in the chat, A and C. So the first option is a perceptron will learn the underlying linearly separable boundary with finite number of training steps. So this is right, that the perceptron will always learn the linearly separable boundary. So it cannot learn quadratic or some other polynomial decision boundaries. So option A is certainly correct. And option B is XOR function can be modeled by a single perceptron. This is not right. XOR function is not linearly separable, so we cannot have only a single perceptron algorithm to model a XOR function. So that is not correct. Option C is backpropagation algorithm used while estimating parameters of neural network actually uses gradient descent algorithm. So this is right. That backpropagation algorithm basically uses gradient descent algorithm. to estimate the parameters of the neural network. So option A and C are correct. And option D says backpropagation algorithm will always converge to global optimum, which is one of the reasons for impressive performance of the neural networks. So this is not correct, that it will always converge to a global optimum point. So it might get stuck into a local optimum point, and it might never get out of that local optimum point. It happens a lot in case of neural networks. So backpropagation does not guarantee a global optimum. So option D is not correct. A and C are the two correct answers here. Now question 2. So this is the XOR table, basically XOR example from the class where we did a transformation of features to make it linearly separable. So which of the following transformations can also work? So this is the table given, and if you simply plot these points, you will see that these points are not linearly separable. So by transforming these points, we can make these points linearly separable. So 4 transformations are given here, and which of these transformations will make this XOR table, XOR function linearly separable? So more than one option can be correct in this case. So you have to try out all 4 transformations given in these 4 options, and you have to pick which of these is or are correct. In this question, you have to simply use all 4 options given, all 4 transformations from these 4 options, and you have to plot those points in a 2D plane to check whether these transformations are making these points linearly separable or not. Srijan is saying option D. Okay. There might be multiple correct answers here, so you have to try out all 4 options and check if any of these options are correct. So Srijan is saying D. I got one answer in the chat. Anyone else? Akriti is saying C. Okay, so I've got 2 answers in the chat, C and D. So in this question you have to try each of these options one by one. So first try this option A. The transformations are x1 dash equals x1 square and x2 dash equals x2 square. So if we do this transformation, so we make another table. So the first point is minus 1 minus 1 minus 1. So minus 1 minus 1 would become 1 1 because we are squaring both x1 and x2, and y would remain same, minus 1. And for the second point, 1 minus 1, it would become 1 1 because we are squaring again, 1. Third point is minus 1 1, so it would also become 1 1, and this y is 1. And fourth point is 1 1 minus 1, so we are squaring x1 and x2, so 1 1 minus 1. So we see that all 4 points have become 1 comma 1. So but the y values are different for different points. So these points are obviously not linearly separable because for the same 1 1 point we have minus 1, and for the same 1 1 point we have got 1. So this transformation would not work. For same point there are 2 different values of y. So this transformation is not making these points linearly separable. So option A is not correct. Then we will try out option B. Similarly we will plot it again, and here the transformation is x1 dash is 1 plus x1, so this would become 0, and x2 dash is 1 minus x2, so this would become 2. Then the second point, so the first point is done. For the second point it would become 2, and it would become 2 1. Then we transform the third point from this table, minus 1 1, so it would become 0, and 1 would also become 0, and this is 1. And then fourth point 1 1, so this would become 2, and this would become 0 minus 1. Now if we plot these points, so 0 2, this is minus 1 point, 2 2, this is a plus 1 point, 0 0 is a plus 1 point, and 2 0 is a minus 1 point. So this is a plus 1 point, this is a plus 1 point, but this is a minus 1 point, this is a minus 1 point. So these 4 points are not linearly separable, as we can see. This is very similar to this OR, that if we plot this table, this sort table, it would look very similar, that the points are not linearly separable. But if we then we have to try option C. Option C is x1 dash is x1 x2, x2 dash is minus x1 x2. So if we plot this, so these are the two answers, C and D. If we plot this option C, where x1 dash is x1 and x2, x1 into x2, and x2 dash is minus x1 x2, I think that is, yeah. So if we plot this, these are the four transformed points that we will get. And now if we plot these points, so first point is 1 minus 1, so let's consider this 1 1 1 1, so 1 minus 1, this is 1 minus 1 point. Then the second point is minus 1 1, minus 1 1, so this is a plus 1 point. Third point is minus 1 1 again, so this point is same, so these 2 points are overlapping. And fourth point is 1 minus 1, these 2 points are also overlapping, this is also a minus 1 point. So obviously we can see these are the 2 plus 1 points and these are the 2 minus 1 points. So simply these 2 points are linearly separable, these 4 points are linearly separable. So option C is correct. Similarly, if you do the transformation of option D, which is this, x1 dash is x1 minus x2 square and x2 dash is x1 plus x2 whole square. See, if you do this, make this transformation, this table would look like this. And again you have to plot these 4 points, these 4 points you have to plot, and if you plot these 4 points, you will see that the points, the positive points and negative points are linearly separable again. So option D would also be correct. So C and D, these are the 2 correct answers, sir. So is this understandable? Is there any doubts or questions?
And 0 for how you are able to make the output as minus in any previous slide also you mentioned 0 2, right? How you create output as
So we are not creating the output, sir. We are not talking about what would be the weights of the perceptron or neural network. So we are trying to find out whether these transformations, these 4 transformations, are making these positives and negative points linearly separable or not.
So, but the question is, for example, can you just go to the previous slide?
Yes.
So x1 dash is 0, x2 dash is 2.
2, yes.
How you will to make it as minus 1?
No, I am transforming this first point, the point that is given to me, this point. This point, the first point of this table. I'm transforming every point. So here the points are minus 1, and the output.
How output is minus 1 for 0 and 1? Because it's a
We are only transforming the input features, not the output levels. Output levels we are not transforming, because by transforming the input features, we are trying to make them linearly separable. Yeah. So linear the transformations are only on the input features. Output levels should remain same for all 4 points. Okay, so we can move on to question 3. So in question 3 is what is the effect of using activation function fx equals x for hidden layers in artificial neural networks. So you have seen different kinds of activation functions like sigmoid, softmax, then ReLU or regularized linear units. These are different activation functions. If we use this activation function fx equals x, basically we are not transforming anything. Just the x what we get from the hidden unit, we are passing that on to the next hidden layer. So this is called linear activation, that we are not transforming the point at all. So this is one kind of activation function. If this activation function is applied to a neural network, what is the effect of that? So there are 4 options. Option A is no effect. It is as good as any other activation function like sigmoid, tanh, all these activation functions that are generally used in a neural network. Option B is the ANN is equivalent to doing multi-output linear regression. So it is saying that it is equivalent to a linear regression, option B. Option C is backpropagation will not work with this activation function. And option D is we can model highly complex non-linear functions using this linear activation function. So which of these four options is correct? So I have already got one answer in the chat. Shankar Lal is saying option B. Option B is ANN is the ANN is equivalent to doing multi-output linear regression. Aravind is saying B and D. Okay. Anyone else? Any other answers in the chat? Akriti is saying option A. So option A is no effect. It is as good as other activation functions. Well, Murugan is saying option D. Option C. C is backpropagation will not work. So the correct answer here is only option B, that ANN is equivalent to doing multi-output linear regression. So the first option says that no effect, it is as good as any other activation function. So this is not right. This linear activation function is of almost no use basically in neural networks. The linear activation function is simply like without using any hidden layer in that place. So that's why it is equivalent to multi-output linear regression. In case of linear regressions, we have this input features and this directly go to this output. These are input features. So there is no hidden layer in case of linear regression, and the same thing happens if we use linear activation function, this fx equals x, in case of hidden layers. So this linear activation function is not as good as other activation functions like sigmoid, tanh. The main objective of applying these activation functions like sigmoid, softmax, tanh or ReLU is that these activation functions bring the non-linearity in the neural networks computation. So if we don't use these non-linear activation functions, the neural network will not learn the non-linear decision boundaries or non-linear model fitting and non-linear regression output. So it would not be able to learn this non-linearity in the output. So this linear activation function will make the neural network completely linear in nature. So output would be completely linear, even in case of classification and also in case of regression. Option B is the correct answer. Option C says backpropagation will not work. This is not right. Backpropagation will work. Backpropagation will work on any kind of differentiable activation function. This activation function is certainly differentiable. So as long as the activation function is differentiable, we can apply backpropagation. And option D is we can model highly complex non-linear functions. So that is the problem with this linear activation function fx equals x, is that this doesn't contain any non-linearity, so it cannot model any non-linear functions. So option D is not correct.
The case even that is the key. Even if we give multiple hidden layers,
Yeah, even if we put even if we
will not be able to.
yeah, so if even if we put this so this is the input layer, so and we put multiple hidden layers and the output layer. So if we apply the linear activation functions into these hidden layers, it would be same as just no hidden layer like this, and all this go to this output, like linear regression or logistic regression in case of classifications. So application of this linear activation functions make this this neural network completely linear in nature. So these hidden layers would mean nothing in that case if we apply this linear activation function. So that's why option D is not correct, that it would not be able to model complex non-linear functions. Question 4. Which of the following functions can be used on the last layer of the neural network for classification? So which of these functions can be applied on the last layer of an artificial neural network for classification? 4 options: softmax, sigmoid, tanh, linear. So multiple options might be correct here. Arvind is saying option A, Sankarlal is saying A, B, C. So only in the last layer we are talking about, that for classification using a neural network, which activation functions can be used in the last layer. Akriti is saying option B. Priya Iyer is saying option A. Tejaswini is saying option A, which is softmax. So the correct answers here are A, B, C. These are the 3 correct answers. So option A is softmax. So we generally use softmax in the output layer of a neural network in case of in case we have more than 2 output levels, and if we have only 2 output levels in case of classification, we use sigmoid. So these 2 certainly can be used for classification. Option C is tanh. So tanh is very similar to sigmoid. The only difference is that in sigmoid, in case of sigmoid, the output value varies from 0 to 1, and in case of tanh the output value is from -1 to +1. Other than that, tanh curve looks very similar to that, similar to the sigmoid, though the equations are different for sigmoid and tanh. But tanh can also be used because the value varies from -1 to +1. In case of sigmoid, it varies from 0 to 1. So similarly, we can use tanh also. But linear we cannot use for classification. Linear can be used for regression tasks using neural networks, but for classification tasks we cannot use linear activation functions in the output layer or the last layer. So option A, B, C, these are the three correct answers.
So, in middle layers, I mean, in between layers, if you use a different activation function, still in the last layer, for example, in middle layers, you use a small or tanks and
Yes.
find the effects of it. That's good.
The activation functions in hidden layers might be different from what we are using in the last layer. It can be like in case of deep neural networks, nowadays ReLU activation function or regularized linear unit activation function is very popular for the hidden layers, but not for the output layer. For the output layer, in case of classification, sigmoid or softmax has to be either sigmoid or softmax has to be used, and in case of regressions, linear is generally preferred in case of the output layers. But in the hidden layers, you can use different activation functions for different hidden layers, so that is not a problem. Question 5. So there is a statement and there is a reason, so you have to answer whether the statement is correct and also whether the reason is correct. So statement is threshold function cannot be used as activation function for hidden layers, and reason is threshold functions do not introduce non-linearity. So this now you have to answer whether the statement is true or false, and also for the reason whether the reason is true or false. This also you have to answer. Statement is that the threshold function cannot be used as activation function for hidden layers, and the reason is that threshold functions do not introduce non-linearity. Sankalal is saying option C, Aravind is saying option B. So threshold function is like this. So for negative values this is 0, and for positive values this is +1. So this is also called the step function. Akriti is saying option A. So correct answer here is option A only. So this is the only correct answer. The statement is true and reason is false. So statement is a threshold function cannot be used as activation functions. So threshold function is not used as activation function in case of hidden layers because it has only two values that it can output, 0 and 1. So this is the threshold function. So this is 0 and this is plus 1. So it doesn't have doesn't output many values. It either gives you 0 or plus 1. So it is not giving much information from the previous layer. So from the previous layer, activation function gives you the value from the previous layer. So it is not giving much information, either 0 or 1. So that's why threshold function is not preferred in case of hidden layers. In case of output layer, it might be preferred depending on the application, but in the hidden layers it is not preferred because 0 and 1, these are the only two outputs it can give. And reason is that threshold functions do not introduce non-linearity. So there is non-linearity involved here, like there is 0 and there is plus 1. So even though this segment is linear, this segment is linear separately, but as a whole this function is non-linear, we can say. So this reason is not correct. The main reason why it is not used is that it doesn't give much diversity in the output. Only 0 and 1, they are the two outputs that it can give.
But how can we say that this threshold is non-linear? Because as the product is tagged, it actually has to be non-linear.
So linear basically means linear would look like fx equals ax plus b. So this is the equation of a straight line simply. Here each segment is linear. This segment is linear, this segment is linear, this segment is also linear. So all these segments, 3 segments are linear separately, but as a whole this function is not a linear function. Similarly, if I don't know whether the ReLU function has been taught in the class, so which is heavily used nowadays. So the ReLU is simply 0 for negative values and just x for positive values. So this red curve, this and this is this is the ReLU function, and this is considered non-linear because 2 segments are linear, but as a whole the function is not linear. So the threshold function is non-linear as a whole. Each segment might be linear. So this is not the reason why it is not used. So the main reason why it is used is because it doesn't give much diversity in the output. Only 0 and 1, these are the 2 outputs that it can give. Not much information we get from the previous hidden layer. So it is not that popular in hidden layers. Now we move on to question 6. We use several techniques to ensure the weights of the neural network are small, like random initialization around 0 or regularization. These things are done to make sure that weights of the neural network are small. What conclusion can we draw if the weights of our neural network are high? So there are 4 options: that the model has overfitted, it was initialized incorrectly, at least one of option A and or option B, and option D is none of the above. So if the weight values are high, what is the conclusion from that? Shankar Lal is saying A, Arvind is saying C, Akriti is saying A, Srijan is saying A. So I've got three answers which are saying option A, and one answer is option C. So the correct answer here is none of the above. So first option says that model has overfitted. So the overfitting is we cannot say that overfitted model should have high weight values. So there is no correlation between these two, that overfitted models might also have very small weight values. So overfitting basically means that it is trying to model even the noise and outlier points which is not necessary. So it is not generalizing well, it is trying to fit or classify even the noise and outlier points. So in that case the model is overfitted, but that doesn't mean that weight values would be very high. And option B says it was initialized incorrectly. So even if the points are initialized incorrectly, doesn't mean it would have high weight values. So we cannot conclusively say that because of incorrect initialization this has happened. So
Is there any weight there will be high weight values?
I'm not able to hear you properly. Can you
What could be reasons? I mean, if there, let's say if there is an ANN and the rates
so yeah, these are the these options are not correct reasons for that. So there might be other reasons, like there is a problem called vanishing gradient problem, and there is a problem called exploding gradient problem. So the exploding gradient means the gradient values are so high that the weight values are becoming very high. So this might depend on the data points, the training samples or training data points. It might also depend on the step size or the learning rate, that the learning rate is very high, so it is pushing the weight values too high. For different neural networks and different applications the reasons might be different, but overfitting is certainly not a reason, and also the incorrect initialization might also not be a reason. So these two are not correlated. So there might be different reasons for that, why the weight values are high. So for this is why we use regularization to make those values smaller. Srijan is saying, okay, so high weights is a necessary condition but not sufficient for overfitting. So there is no correlation between overfitting and high weight values. So overfitting doesn't mean it would have high weight values, or also high weight values doesn't mean it might overfit. So there is no association between overfitting and high weight values. So because the definition of overfitting is completely different from high weight values. The model might have high weight values, still the model might be underfitting, or even the model might be perfect, very accurate, but still it might have high weight values. So these overfitting and high weight values are not correlated or associated. Question 7. Which of the following are true when comparing ANNs and SVMs? So option A says ANN error surface has multiple local minima, while SVM error surface has only one minima. Option B says after training an ANN might land on a different minimum each time when initialized with random weights during each run. Option C says as shown for perceptron there are some classes of functions that cannot be learned by an ANN, and SVM can learn a hyperplane for any kind of distribution. And option D says in training ANN's error surface is navigated using a gradient descent technique, while SVM's error surface is navigated using complex optimization solvers. So multiple options may be correct here. Arvind is saying ABD. Anyone else? Sankalal is saying ABD. Okay. So the correct answers are A, B and D. So both of you have written correct answers in the chat. So option A says that ANN error surface has multiple local minima while SVM surface has only one minima. This is correct. ANN, because there are many the weight parameters in the neural network, so the error surface is very rough like this, so it can have multiple local minima points, and it might get stuck in any of these local minima points. So there might be multiple local minima in case of ANN, but in case of SVM there is only one local minima which maximizes the margin. So that is the only objective in case of SVM, that whichever straight line that maximizes the margin, or the hyperplane that maximizes the margin, and there is only one possible hyperplane that can do that. So there is only one minimum point. And then option B says after training ANN might land on a different minimum each time when initialized with random weights during each run. So if we pick random weight values, in that case on each run it would give different output, and it would land on a different minimum. So it might get stuck in a local minima point if we randomly initialize the weight values on different runs. So option B is also correct. Option C says as shown for perceptron there are some classes of functions that cannot be learned by ANN, as SVM can learn a hyperplane for any kind of distribution. So this is not correct. That it is well known that ANN is a really good function approximator. It can approximate theoretically any function that is given to it. So this is not right. Option D is in training ANN's error surface is navigated using a gradient descent technique. So this is right. So we use gradient descent for a neural network backpropagation algorithm, and SVM's error surface is navigated using convex optimization solver. So this is also correct. So convex optimization solvers are used for finding out the minima for the SVM error. Option D is also correct. So A, B, D, these are the three correct options here. So now question 8. So you are given the following neural networks with which take two binary valued inputs, x1 and x2. So both x1 and x2 take values from 0 and 1. So only 0 and 1 are the possible values for both x1 and x2. And the activation function is threshold activation, hx equals 1 if x is greater than 0 and 0 otherwise. Which of the following logical functions does it compute? So this neural network computes a logical function or logic gate like OR, AND, NAND, NOR, NOT. So these are the different logic functions or logic gates. So this neural network computes any of these logical functions. So four options are given: OR, AND, NAND, and option D is none of the above. So basically you have to compute the output for this neural network for every combination of x1 and x2 values, and then you have to say which logical function is that. So I have already got two answers in the chat. Aravind is saying option A, which is OR, and Sankarlal is saying option B, which is AND. region is also saying option A. Akriti is saying option B. So for this question, we have to compute the output for different inputs. X1, X2, these are the inputs, Hx is the output. So these are the possible combinations of the input features, because both the input features are binary valued inputs. X1 can take only 0 and 1, and X2 can also take only 0 and 1. So for the first input 0 0, if we compute this Hx, so this is simply 8x1 plus 8x2 minus 4. This is what we have to compute, and then we have to compute whether this quantity 8x plus 8x2 minus 4 is greater than 0 or not. If it is greater than 0, then the Hx is 1. If this is less than 0, then Hx is 0. So for the first input 0 0, so it would be minus 4, so negative, so this would be 0. Then for 0 1, it would simply be x1 is 0, x2 is 1, so it would be 8 minus 4 4. So Hs would be 1, because this quantity is 4. Similarly for 1 0, it would also be 1, and for 1 1, it would be 8 plus 8 minus 4. So that is still positive. 16 minus 4, which is 12, so it is positive. So if that quantity is positive, then Hx would be 1. So now if we compare this truth table with different logic functions, so we will see that it is similar to OR gate, that if any of x1 and x2 is positive, is true, then output is also true, and when both the inputs are true, output is also true. So this is nothing but OR gate, and option A is the OR gate. So option A would be the correct answer. So is there any questions or doubts in this question? Okay, so we can move on to question 9. So choose the correct statement, multiple may be correct. So this is on parameter estimation. So option A says MLE, or the maximum likelihood estimation, is a special case of MAP. MAP is maximum a posteriori estimation when prior is a uniform distribution. So MLE is a special case of MAP when prior is a uniform distribution. Option B is MLE acts as regularization for MAP. Option C says MLE is a special case of MAP when prior is a beta distribution. Option D is MAP acts as regularization for MLE. So multiple options may be correct here. Akriti is saying B and D. So B is MLE acts as regularization for MAP, and D is MAP acts as regularization for MLE. Okay, so B and D are two contrasting options. So both the options cannot be true at the same time. So correct answers are A and D. So A says that MLE is a special case of MAP when prior is uniform distribution. So basically in MLE we try to maximize the likelihood, which is probability of x given theta. So we try to maximize this thing with respect to theta, and in case of MAP we try to maximize a posterior distribution, which is theta given x with respect to.
Can you please explain? I am still what where you are using MLE. Just maximum nuclear, maximum nuclear. Can you just explain?
It would be difficult to explain the whole thing. I mean, in the week 5 video lectures, these are already given, that where to use MLE and how to use MLE, and what is MAP and how to use that. So in case of, I mean, these are parameter estimation methods. So this is the likelihood, probability of x given theta. We are trying to find out the theta value which maximizes this likelihood. So in MLE we try to maximize this likelihood function, a likelihood probability distribution, probability of x given theta. And in case of MAP, or maximum a posterior distribution, we try to maximize the posterior distribution, which is probability of theta given x, which is same as probability of x given theta into probability of theta. Simply we use the Bayes theorem to compute that. So this is there in the MLE also here, that this is the likelihood, and the extra term p theta is the prior distribution of the parameters theta. So this p theta, actually if this p theta is uniform, so we can remove this p theta in that case. Then the MAP becomes MLE only if this p theta is uniform and it is known beforehand. So this becomes same as MLE estimation. So option A is correct from that. And option D says that MAP acts as regularization for MLE. So this is actually right. So this prior distribution acts as regularization for the MLE estimator. So if we have some prior knowledge about the values of the parameters theta, we can apply those the prior values here in this p theta, and it would act as a regularization for this likelihood estimator px given theta. So option D would be the correct answer. So these things are given in the video lectures, so you can go through those video lectures again. So the definitions of MLE and MAP are given there, mathematical definitions, and it will be much more clear if you go through those video lectures again. So correct answers are A and D here. Question 10. So suppose you have inputs x, y and z with values -2, 5, -4 respectively, and you have a neuron q here, q is here, and neuron f is here, with functions q is x plus y. So this plus sign is given here. So q is simply adding x and y, and f is multiplying this q and z. So this multiplication sign is given here. So these are calculating these arithmetic operations. Q and f are calculating these arithmetic operations. So what is the gradient of f with respect to x, y and z? You have to compute the gradient of f with respect to x, y and z. So basically you have to compute this delta del f del x, del f del y and del f del z. These are the three quantities that you have to compute, and the values of x, y, z are given. So -2, 5, -4. So the values are given for x, y and z. So you can actually find out the values of these expressions. Srijan is saying -28.3. So here f is q into z, so which is x plus y into z. So if I find the derivative of f with respect to x, it would be z, so it's z, yeah, this is only z, because this is x into z plus y into z. So this is x into f is x into z plus y into z. Now if I take the derivative of this with respect to x, this yz term would produce 0 only, because there is no x term in this yz. So only derivative comes from this xz, which is z, x cancels out, so z remains, and z is -4. So the first one would be -4, so this is -4. Now similarly, if we take the derivative with respect to y, so the derivative of xz, this would be 0 with respect to y, and derivative of yz would become z only, so which is again -4. And then finally derivative with respect to z, so f is q into z, so the derivative with respect to z would be only q, and q is 3 here, because q is sum of x and y. X is -2, y is 5, so q would be x plus y, which is q 3, so this would be 3. So this is -4, this is -4, this is 3. So -4, -4, 3. These are the three correct answers. Yes, Region has corrected his answer. So -4, -4, 3, and Akriti has also written -4, -4, 3. So yeah, this is the only correct answer here. Now question 11. So in training a neural network, we notice that loss does not decrease in the first few starting epochs. What is the reason for that? So the loss is not decreasing for few epochs. What might be the reason for that? So there are four options. The learning rate is low, regularization parameter is high, stuck at local minima, all of the above could be the reason. Sankarlal says option C, which is stuck at local minima. So here the correct answer is D, that any of these three might happen. That if the learning rate is very low, it might not decrease for the first few epochs. And if the regularization parameter is very high, so it is the gradient descent algorithm is giving much more importance to the regularization factor rather than decreasing the actual loss function. So in that case also the loss function might not decrease, and option C is an obvious answer, that it might get stuck in a local minima initially, so it is not able to get out of that local minima point, so that's why it is not decreasing. So all of these could be the reasons for the loss function not decreasing. So option D is the correct answer. So these were the problems that I wanted to discuss in this session. If you have any other doubts regarding any of the problems discussed today, or any topics covered in this week's lectures, you can ask me. So if there are no other questions or doubts, then we can end this live session. Thank you everyone for joining. We will again meet next week.
Thank you.
Thank you.